In the spring of 1930, a 24-year-old astronomer named Clyde Tombaugh spotted a tiny anomaly on a photographic plate. He had discovered what the world eagerly accepted as the ninth planet of our solar system, Pluto. But almost immediately, the observational data presented a massive problem. While the other 8 planets circle the Sun in nearly flat, concentric rings, Pluto's path deviated sharply from the standard. It follows a highly elliptical orbit, tilted 17 degrees off the plane of the rest of the solar system. Despite these glaring orbital red flags, Pluto retained its planetary status for decades. Telescopes of the era simply couldn't capture enough detail to tell astronomers exactly what this distant, dim object actually was. Because the scientific community expected to find a ninth planet in that region of space, they classified it as one. By prioritizing expectation over observation, they created a taxonomic time bomb that would take 76 years to detonate. That collision between definition and reality finally arrived in August 2006, when the International Astronomical Union convened in Prague. Their task was to establish, for the first time, a strict mathematical definition of the word planet. On the final day of the conference, roughly 400 astronomers raised their yellow voting cards to pass a sudden resolution. Pluto was officially stripped of its title and reclassified into a newly invented category, the dwarf planet. The public backlash was fierce. People had grown up with 9 planets, and nostalgia fueled widespread resistance to the ruling. Petitions circulated, and classrooms across the globe questioned the sudden change in their textbooks. This raises a fascinating intellectual conflict. Can a democratic show of hands by a few hundred people alter the physical reality of the solar system? Or is this just the messy process of science struggling to categorize an evolving universe? To understand why Pluto lost its status, we have to look at the 3 criteria the IAU established in that 2006 vote. Rule 1. The celestial body must orbit the Sun. Pluto passes easily. Rule 2. The body must have enough mass that its own gravity pulls it into a nearly round shape. Again, Pluto passes. Rule 3 is where the controversy lies. The IAU declared that a planet must have gravitationally cleared the neighborhood around its orbit, meaning no other objects of comparable size can share its path. This visualization shows where Pluto fails. It shares its Kuiper belt path with hundreds of trans-Neptunian objects. Expanding inward reveals a flaw. Jupiter shares its orbit with 100,000 Trojan asteroids, and Earth with 10,000 near-Earth objects. Neither has fully cleared its neighborhood. The clearing the neighborhood requirement is heavily dependent on distance. The further an object is from the Sun, the more massive it needs to be to sweep its orbit clear. The rule judges a body by its location, rather than its physical composition. For nearly a decade after the vote, astronomers treated Pluto as a simple piece of icy debris. Then, in 2015, NASA's New Horizons spacecraft completed a historic flyby, capturing the first high-resolution data of the world. The imagery returned by New Horizons revealed a surface defined by towering mountains, vast plains, and a massive heart-shaped basin of frozen nitrogen. They also discovered Right Mons, a peak soaring 4 kilometers high with a massive central depression. It operates as a cryovolcano, an ice volcano that erupts a thick, slushy water ice mush instead of molten rock. Further thermal modeling suggests Pluto harbors a deep liquid water ocean beneath its crust, driving active geological processes that constantly resurface the planet with shifting plates of ice. To some planetary scientists, including Dr. Philip Metzger, this discovery of active geology and nitrogen ice flow makes Pluto more complex than Mars. In their view, this diversity of landforms makes Pluto the most dynamic world in the solar system after Earth. In response to the New Horizons data, a massive contingent of planetary scientists proposed an alternative to the IAU's orbital mechanics approach, the geophysical definition. This definition relies on just 2 criteria. First, the body must be smaller than a star, meaning it has never undergone nuclear fusion. Second, it must possess enough self-gravitation to pull its own mass into a spherical shape. This scale comparison charts every known round object under 10,000 kilometers in diameter. If the geophysical definition is adopted, it instantly elevates over 100 known celestial bodies, including Pluto, the asteroid Ceres, and our own moon, to full planetary status. The geophysical approach prioritizes intrinsic properties, the actual physical structure and geology of the world, over extrinsic properties, like the specific piece of orbital real estate it happens to occupy. Today, the debate continues between two distinct scientific camps. Astronomers tend to prioritize gravity, mass, and how objects interact in space. Planetary scientists prioritize geology, structure, and what happens on the surface. Neither definition is factually incorrect. They simply serve different scientific disciplines that are looking for different answers. This ongoing friction highlights exactly how science is supposed to work. It is a rigorous, evolving process of constant recategorization based on new evidence, not a static list of memorized facts. Whether the textbooks call it a planet, a dwarf, or a Kuiper belt object, the complex reality of Pluto remains exactly the same. It forces us to continually question how we observe, define, and understand the universe around us.